Very good morning to all the students. Let's begin today's lecture of digital communication. I hope my voice is properly audible.
Yes, sir.
Yes, sir.
Thank you. So, to begin with, there is a little correction in what we discussed yesterday. A little correction regarding the digital interpretation of bits in your delta modulation. Okay, so I just wanted to bring it to your attention. Let me share my screen, and I also hope you people have started writing your lab assignment 1. So I'll create the link. 12 is the deadline. No, sorry. This Saturday I have kept it as a deadline. I have extended it, and today I'll create the link. So please upload it. You have today's and tomorrow's time to do so. Similarly, we will also see code for frequency modulation, and the same you are supposed to submit in the next weeks of time. Okay. Just a moment, I am sharing my screen. Okay, is the screen visible?
Yes, sir.
Okay, so regarding the digital interpretation of this delta modulated signal, there is little correction. I told you about this levels. Please do not consider that. Rather, the digital conversion is actually relative. Relative means the comparison between the current value of the signal MT and the sampled value of the current output generated by the system. We take into account, we take the difference based on the sign of the difference. If it is positive or negative, we are deciding to have a addition or subtraction of step size. Okay, that is the delta modulation concept. So whenever it is not like it is converted to digital domain, that is not the right way. When if you compare with this reference, suppose this is the current quantized value, then based on its comparison, if it is having a increment in step size, so if plus delta is added, that is regarded as a 1. Now after this, if you compare this with the previous one, this one, there is a decrement, so it will be a 0. Similarly, when again it is incrementing, it is 1 during this duration. So this is actually done with this reference. Okay, so all these time durations, they have their bit representations like this. So what will come here? Can somebody tell? During this duration, what bit will be transmitted? What should I write?
1.
1. Then again?
Again 1.
Okay, 1, 1. Here it will come 0 because there is a decrease in step size. So that was one little correction, and please make a note of it. Okay, are we good? Then again, so this will be 1, this will be 0, 0, 0, 0, 0, 0. So it will be like long trail of zeros. So please respond. Is it okay?
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay. And yeah, so let me share with you people. So the code for frequency modulation I'll share in the end. What I've done is just to have a quick revision and a different perspective of what content we are going through in this digital transmission of analog signals. I have prepared actually I collected my old slides, introduced some new material to it, and I prepared, and I will just quickly go through that revision process. And during that revision process, some of the topics will be new in there. Yes, so it will like kind of a revision. Okay, so let me share my screen again with the new slide. Okay, is the screen visible? Students, screen visible?
Yes.
Yes, sir.
Okay. So this is just outline of this kind of, now it is acting as a revision, but earlier I used it as a main slide. So we have seen PCM, sampling, aliasing, quantization, encoding. Then we have seen different line codings. We will see some numericals about also this line codings. I will ask you. Then we'll take differential PCM, DPCM, and delta modulation also we have seen. So majority of the topics we'll quickly go through. I hope it will help you, kind of revise and strengthen your learning. Okay, so this is all about information, how it is in different forms, and it is a function of continuous variable time t. T is the independent variable. So when we are transmitting analog signal, analog information into digital format, popular choices are PCM. We have seen differential burst code modulation. We'll see that is remaining, where we do not send the exact value of the signal, rather we transmit the difference of the two signals, and then we have a delta modulation. Okay, so there are certain advantages of digital format. I think you all can read it, and I mean they are very self-intuitive in nature. So digital has its own advantages, and how you can tackle problem of distortion, noise interference, signal mixing, multiplexing, etc. All these you can achieve using digital format. So I hope if you read this slide, it will be fine. It will be okay. Will that be understanding okay? These are simple advantages. Okay. So please go through it. Then this is a block diagram of digital communication system. Here important is to understand this source coding, channel coding, and line coding. Okay. So you can see your information source is there. It is source coded, and then channel coded, and then line coded. What does this meaning of source, channel, and line coding? So you can see source coding consists of your analog to digital conversion, compression, encryption, remove redundancy if you have repetition or unnecessary data, or which you feel that if you transform your data into some other format, you can get rid of chunk of data. Okay, so can somebody tell where we use compression? Let me ask from Drupad Chauhan.
Yes, sir.
Can you recollect where we have seen usage of compression in our earlier lecture? Sorry?
Actually, sir, I don't get
Okay, you do not. It's okay. Please, Ankita. Okay, Nidhe Pancholi, you raised your hand.
Oh, yes, sir, that was my mistake.
But you can answer, Nidhe.
Okay, yeah. Non-uniform quantization.
Yes, very good. So in non-uniform quantization, we have seen usage of compression, where we were providing a non-linear characteristics, introducing a compressing system, compressor, which will give what? Less weightage to the amount of variation in the higher level input signal values in comparison to lower level input signal values. So we have seen that. So when you are having this ADC, encryption, compression, redundancy removal, you're calling it as, collectively calling it as source coding, because the source information you are transforming. In channel coding, what processes are involved? Those are error control, framing. Framing means forming frames out of group of data, group of bits. You are introducing redundancy. Now this is conflicting. In source coding, you are removing redundancy. In channel coding, you are introducing. Since am I audible?
Now you are audible, sir.
Okay. So I hope you were able to catch what I said last. In source coding, you are removing redundancy. In channel coding, you are introducing redundancy. First of all, what is redundancy? Can somebody tell? So redundancy is unuseful or extra unnecessary things. Those are redundant. Redundant things can be removed. Okay, they are not usable. So in source coding, our aim is to achieve good performance. Good performance means if you can remove unnecessary bits, unnecessary information, that will help you transmit more data. That is the aim in source coding. Whereas in the aim of channel coding, what is there? Error control. You want to, because error will happen when you will transmit the data over channel, error will happen. Now, when you receive it, first you have to detect whether any error has occurred or not, first thing, and then you need to correct it in case if any error has occurred in the data. Error might come due to noise, channel characteristics, etc. So what we do when we are transmitting over channel, we are introducing redundancy. Now introduction of redundancy means addition of additional bits, addition of redundant bits to your actual data. What will it do? The probability of occurring error on your actual data bits will be less. The probability of those redundant bits getting affected by noise will be there. So they will, take a part of the blow which might be given by the noisy signal. Okay, so if you are having 5 actual data bits, okay, and if you are adding 2 bits to it, just redundant bits, they are not conveying any information. So in total, you are transmitting 7 bits. Now, if any noise or any interference occurs, it is probable that those 2 bits will take the blow. Okay, so the actual data bits will not be affected. So it is actually running on the principles of probability of error. So when you add redundant bits, the probability of occurrence of error on the actual data bits get reduced. Hence, it is known as introduction of redundancy. Hello. Yeah, one phone came in between. Now, am I audible?
Yes, sir.
So is this clear? Removal of redundancy in source coding, introduction of redundancy in channel coding. Is this clear?
Yeah, sir, is this something to do with parity bits as well?
Parity bits, yes, they are done to detect and detect any error whether it has occurred or not. So we'll cover up all these topics. We will see the different schemes that will come in Unit 2. When information theory and coding part will come, we will dive into much details. One bit error detection schemes, multiple bits detection, and then if we have detected error, how you can correct it, how to identify which bit has gone haywire, right?
Okay,
So,
sir.
but you just keep in mind redundancy, not only removal but also introduction helps us in our communication system, but at different stages. And line coding, we have seen it. It is actually the electrical waveform of the equivalent bits. So it is a digital signal where you transmit different voltage levels depending on your line coding scheme. Okay, and they have made with compatible with your modulator. So this is, you can see, carrier modulation. So carrier modulation, if you are going for not baseband communication, you are going for carrier modulation communication. You are using some high frequency carrier and then transmitting over channel. So this is exact the reverse operations you will perform: carrier demodulation, line decoding, channel decoding, source decoding, and then the destination actual information will come to you. So all parts are very important. Source coding helps you have a better bandwidth utilization. If you are sending less number of bits, it is good, right? But at the same time, channel coding is also essential when you have long range communication. You have noisy channel, how to tackle, because noise will definitely happen. Noise will definitely affect your signal. And then different line coding schemes and all. Okay, so I think it is okay. Shall we move forward? We move forward. Now, what are different performance criteria in any digital communication system? How do you qualify or quantify the performance of your digital system? So as I mentioned, probability of bit error, PE, or bit error rate. It is also popularly known as BER, bit error rate. Then you have normalized signal to noise ratio measurement. Signal to noise ratio is actually signal to noise ratio per bit. Okay, how much signal level and how much noise level is there? We represent it. We represent the signal like this, but essentially it is some noise will happen, no? So the signal will become like this. Okay, so the actual signal level and the noise signal level per bit, how much it is, that is represented by EB by N naught. And this is useful when comparing bit error rate performance of different digital modulation schemes. So we'll see all these in detail. And EB is the signal energy with regards to a particular data bit, and NO is the noise. PSD. What is PSD?
Power spectral density.
Power spectral density. And what is EDS?
Energy spectral
What is
density.
EDS, yes, energy density.
Spectral density. Yeah.
Yes, spectrum. Good. Now, what are the goals should be there in communication system? So we will want all the good things. We don't want bad things. So these all are bad things. These all are good things. Best transmission rate, highest data rate, best system utilization, U. So RU. Least bit error rate. Okay, least bandwidth requirement. One thing is bandwidth availability. One thing is bandwidth requirement. So, I mean, with regards to bandwidth requirement, it should be least. With regards to availability, it should be very high. To minimize system complexity. Like we have seen no PCM has so many blocks, whereas delta modulator had very less blocks. So system complexity definitely was simple in DM in comparison to PCM. Likewise, so different system will have different complexity, not only in terms of number of units, but also in terms of the timing performance, the timing requirement for getting set up your system, and minimize required power. So I think this is pretty much clear. PCM system we have already seen. Okay, so we have sampling, quantization, then encoding, and we transmit like this. So here I have tried to include a few equations. MT is your original information signal. First it is sampled and then quantized. So the output of sampler, you can see we have represented, instead of MT, now it has become M and TS. M are integer values. Okay, so T is NTS, M and TS, the output of sampler. Okay, I hope it is very clear. Fs is our sampling rate or sampling frequency. It is the inverse of time period, sampling time period, TS. Okay, this formula is also we have discussed. Quantizer converts each sample into different values that is closest to it from among a pre-selected sets. Pre-selected set means levels, different levels of which we are talking. It selects, quantizer selects one of those levels and assign to the nearest level. Then encoder represents it into some R bit code word. Okay, so we have seen one example where we had 8 levels. So how many bits we were using? 3 bits. So based on the level of the signal which was quantized, we were transmitting those many number of bits. So if level 0 was identified, how many bits? 3 bits, and each having 0, 0, 0 value. If the level was 7, all the bits were 1, 1, 1. Okay, this forms our bit stream. So this bit stream we have formed, and that has to be properly transmitted. So at this, till this level, it is a logical level, right? But then you move to next level using line coding to the equivalent electrical signal transmission. So Fs is your sampling rate, R bits per code word. So if you look at the actual bit rate of the PCM system, it is actually R into Fs, or R upon Ts bits per second. I hope it is clear. Why is it so? Because each level we are representing with particular code word. That code word is taking a particular amount of bits. So with regards to your every sample which you take at the rate of sampling rate, you have that much number of bits per code word. Okay, are we good?
Yes, sir.
Okay, and then at this receiving side, you have decoder. It converts this R bit code word into corresponding discrete amplitude values, quantized values, and then you use a spatial filter you call as reconstruction filter, which will give you an estimate of your original signal. You can see this cap signal is there, M cap T. So M cap T is actually estimate of your original signal. Okay. So if provided if there are no channel errors, your estimate M cap T will be nothing but equal to MT. But this does not happen. Errors come, we need to get rid of it, and in that process our system has some performance criteria. We have also seen sampling theorem. That's not all written here. I think you can go through Nyquist rate. All this we have discussed. Then this is ideal pulse sampling. I just wanted to bring it to your notice. This we have already seen. This is some band limited signal. You are sampling with regular impulse, regular interval occurring impulses, and this is the frequency domain representation. So I mean, I don't want you people to learn it, but just have this fact. It is not going. Okay. So the corresponding Fourier representation, frequency domain representation of this sampling process is nothing but this one. Okay. I hope you remember convolution in time domain is multiplication in frequency domain. Okay. Multiplication in time domain is convolution in frequency domain. I hope you can recollect. Yes or no?
Yes, sir.
Hai. So this is all those the simple concept. It is just for your information. I will not ask all the derivation like this. So all these sampling and its frequency domain representation, you can have a look. Anti-aliasing, we have seen aliasing effect of aliasing when there is a problem with your sampling rate. When you undersample it, you get loss of information. You need some anti-aliasing filter to get rid of it. Now here we are assume that there is some band limited signal, and if any higher frequency signal comes, it will result into aliasing effect. So we need to get rid of it. So how do we do it? We use an anti-aliasing filter. Anti-aliasing filter is a low pass filter with a cutoff frequency like this. These are some practical sampling rates, like for speech, audio, and video. Just there are some values. Just had a look at it. So I'll share this PDF after today's lecture. You can go through it. So video obviously will have high bandwidth requirement because you are sending some frames per second. Every frame is having some size. Say for example, if a picture is 640. Yeah, there was some network issue. Are we good? Am I audible? Am I audible?
Yes, sir.
Okay. So I was telling you about the video specific case. Suppose you are transmitting a 640 cross 480 resolution video, and then these many number of pixels will be there. Assume that you represent each pixel with 8 bits. So into 8 bits. So see how much how much amount of data is there in a video. So that's why your bandwidth requirement is very high in case of video. Audio, it is actually decided by our human hearing perception. So you can see we can hear up to 15 kilohertz. So CD quality audio, they are sampled at 44 kilohertz. Okay, likewise. Then three forms of analog baseband pulse modulation we have seen: pulse amplitude modulation, pulse width modulation, and pulse position modulation. So in PAM, you have amplitude of pulses. They are varying with respect to your actual signal. Pulse width modulation, where the width of the signal, width of the pulses, they vary as per the amplitude of the analog signal. Pulse position modulation, position of pulses, it varies as your amplitude of information signal. So this is just, so this is your actual signal, and in PAM, exactly pulses will take the amplitude value in accordance with the actual signal value. In pulse width modulation, or it is PDM also, it is represented. So you can see wherever the amplitude is more, you have larger widths. When the amplitude is very small, you can see the width is changed. In pulse position modulation, you can see the pulses are farther. This distance, this time duration, the time difference between two pulses is actually decided by the amplitude level. Amplitude level is highest here, so you can see this duration between two pulses is like this. But when amplitude is decreasing, here you can see frequently these pulses are occurring. This is pulse position modulation. Then a simple circuit for generation of pulse width modulation. You use a comparator along with sawtooth generator. Sawtooth signal, I hope you all have seen it. Yes, sawtooth signal. Am I audible?
Yes, sir.
Okay. So how do you generate pulse width modulation? Just a simple circuit for that. This is your actual signal fed to the, this is the operational amplifier. I think you are all exposed to operational amplifier. Yes?
Yes, sir.
है ना? So there are two inputs into operational amplifier, inverting and non-inverting. This is inverting, this is non-inverting. So in the non-inverting terminal, you give your original signal, and in the inverting terminal, you are giving a sawtooth signal. So this sawtooth signal is going to this inverting terminal, and it is a comparator circuit. So it will produce the equivalent difference of these two. So the GT minus sawtooth, whatever it will be there, it will be the output. So you can see this curve, this red, I am painting it now. This one, this is our original GT. Okay, so you can see whenever your sawtooth signal level is less than your original GT, you have a output, you have a positive output, because here you can see, because the output is GT minus sawtooth signal level. So whenever GT is high, more in comparison to your sawtooth signal level, you will have some output here. So here you can see in this range, your GT is value is more than this sawtooth signal level. So you have some output. But after this instant, sawtooth signal increased and the difference becomes negative. So you are getting nothing, its output. Okay. Again, at this instant, the sawtooth signal level dropped and is less than the original GT signal, and it is going till this point. Okay, like this. So the width is actually dependent on how much time duration is there between these and these time instants. So here this you can see, because of the slope of this curve, for a larger duration you have positive output, you have difference output is coming as positive for this comparator, hence this output is this much wide for this duration. Okay, so in this manner you can see width of these pulses is changing with a simple circuit like this. Okay, is it clear to everyone? Okay, so I hope it is clear. PPM is simply obtained using monostable multivibrator MVV and feeding PWM as the input to it. Quantization also, we have seen L levels and how many bits you are using to input those quantization levels. This is the example of pulse code modulation. Okay, so these are the sampled values. Then you have number of quantization level. In this case, we have 4 quantization level, 0, 1, 2, and 3 quantization level. So we start with sample T at 0. It has 0 amplitude and it corresponds to 0 level. So we have assigned in red color, you can see 0 level. Next sample is this value 1. Exactly, it is falling at the level 1. So we have assigned level number 1. Next sample near to level 2, but are not exactly equal to level 3. Okay, but it is closest to which one? Level 2. So we have assigned level 2 and waiting for next level. Now next level is near to level 3, this sampled value. So we will assign the level 3 like this for this entire duration. Next sampled value like this. So we obtain this signal. Okay, so based on your sampling rate, you are having quantized values. So we represent this as 0, 0, 0, 1, 1, 0, 1 1. So this will form our bit stream to be transmitted. Okay. Each quantization level represents different combination. The effect of number of levels in quantization. So this is these many levels. So however, if you increase the number of quantization level, the quantization error is reduced. Obviously, you have better approximation to the actual signal if you increase the number of levels or if you increase the decrease the step size. This also we have discussed earlier, like this. Okay, here you can see this. So you have better approximation of the same signal in this case in comparison to this one. Okay. So we have also seen formula for quantization error. In that example, we have assumed this VH and VL. VL means the lowest value of the signal. VH means the highest value. There we have assumed MP and minus MP. Okay. So that came around 2 MP by L step size. But here it is delta is VH minus VL by L. This is another formula, but same. If you have VH as MP, VL as minus MP, it will also come the same way. So don't get confused, the same thing. So, and all those things we have written. This also we have discussed. What is the quantization error? Difference in the actual value and the quantized value. Okay, and with we have assumed that the quantization error, it is properties of uniformly distributed in the range step size minus delta by 2 to delta by 2. Okay, I hope you recollect. So we assume all the values of the quantization error in this range minus delta by 2 to delta by 2. Total kitna ho gaya? Delta is uniformly distributed. So each value has equal probability of occurrence. Which value? Quantization error value. Okay, so each value in your quantization error has a probability of 1 over delta, because delta is the total width of the minus delta by 2 to delta by 2, how much it becomes total magnitude delta. So each value has 1 over delta as probability. Why is it so? Because if you remember, area under the curve should be unity, if you recollect. So delta is this total range, and this level of probability is 1 by delta. Since it is uniform distribution, a delta into 1 by delta becomes unity. Okay, that's why this is there. So I hope it is okay. Please say something, students.
Yes, sir.
Okay. Then this we have seen this formula, and this you have to remember. Okay. Mean squared value of quantization error is delta square by 12. Okay. Then this special case where we have assumed a signal which is a single tone sinusoid. It is a sinusoidal signal. It can be cos or it can be sine. In that case, what will be the formula? So if you solve it, you will get signal to quantization noise ratio as 3L square by 12. Okay, you just go through it. If you find any difficulty, we'll discuss it. Okay, I think we stop here and we'll continue with our revision exercise next week. Now I take you all to our Scilab code so that you can submit the lab assignment 2. Is this screen visible? This code is visible?
Yes, sir.
Hanji. So you can see we have created different values for sampling frequency, then time instants we are creating in Scilab, we are denoting different carrier amplitude, modulating signal amplitude, carrier frequency, modulating signal frequency. Then we are forming the carrier signals and modulating signal with the help of this simple equation. And then we are assigning some value to the modulation index, which is represented as beta in FM. Okay, if you recollect. So we have assigned 8 as value of that modulation index. And then finally we are forming FM signal with this equation. So A cos, and inside this cos everything is there. So A cos 2 pi FCT plus M or beta. Okay, M we have written here because beta symbol is not represented in Scilab. So beta into AM sine omega mt. Beta into your actual message signal, beta mt. Okay, and when you plot it, you will get the FM signal. Very simple code. I just execute it. And is the graphics window visible?
No,
Yes.
sir.
ये आपको plots दिख रहे हैं?
No, sir.
No, sir.
No?
No, sir.
Okay. Now?
Yes.
So you can see this is our modulating signal, this is carrier signal, and the frequency, this FM signal is having characteristic frequency varying with respect to amplitude of the modulating signal. Okay, I hope you are through with that AM part. AM, generation of AM, generation of FM. FM today we have seen, AM I think you all people have started to prepare the report. Any difficulty in that? In AM part? Because I will strictly follow the deadline. This was the code for AM and this is FM. Okay.
Sir, the AM code is running properly,
Okay.
but
Okay. So yes, so all students, they should just have a look at these file, and I'll share the screenshot of this. Wait. Just a moment. So this is your AM code, and AM code I think I have shared, no?
Yes, sir.
I have shared, yes. FM I should share now. So any student faced any difficulty in installation of Scilab or something like that, please report it now. There should not be any actually.
sir, also I want to ask, in the assignment part, do we have to submit the screenshots too?
I mean these plots you are referring to, Chirag?
Yes.
No, you can not screenshot, but you can save these like this. You can export it. If I run this, yeah. So here you can see file, export to or copy to clipboard. You can save as JPEG. If you save it, you can save. If you export to it, you can as PNG or JPEG, whatever you want. You can save that, and you just insert this JPEG and PNG file into your report. So report should be PDF file only. While preparing your PDF file, I have told you, handwritten. It should be handwritten. Hello.
So, sir, the PDF file should only contain the code of handwritten code. That's it.
Not code. The how you write your file, no project file. Sorry, lab file.
Yes.
You have to write. I've discussed that format, title, and all those things, and then you all have to write with hands, and there is a reason behind doing, making you do so, because in that process you will do it and you will remember it, and once you write your handwritten this lab assignment, insert this JPEG file into your PDF something. So I hope there is no issue with that. है ना?
Yes, sir.
Yes, sir.
Okay.
There's.
ठीक है. So I think we stop at this point of time. If you have any query, anything, please feel free to ask, and I'm taking attendance. So you all people are getting comfortable with digital communication. Anything if you want to share, please feel free. You are enjoying it? Yes, please respond. Devang, you said for very short, pulse duration. What you said? Like a pulse.
Sir, I am enjoying, but sometimes I am difficult in this subject.
You can stop me that moment. If you have any query, you feel free to stop, sir, please can you explain it again?
Yes.
That's why I ask you all again, are we good, and so etc. Like that is the only reason. ठीक है. So if no further queries, thank you everyone.